This is April 10, 2013, and the lesson for today started out with a do now that looks something like this. What powers of 10 are you going to have when you have this number right here? So let's go back and look at an example that I gave to the class and see if we can make sense of this. When we take a number like a decimal of this sort and we say we want this to be in scientific notation, you would know what to do. Well, that's what we're doing. We're figuring out what the power of 10 will be, and the 4, of course, is multiplied by that power of 10. So we count the number of zeros. We have 1, 2, 3, 4 zeros, and then we have another number. So to get the decimal here, which is what we want a one-digit number, or a one-digit number with whatever number of decimals will be after it. So we're going to move this 1, 2, 3, 4, 5. And that's where this number is going to come from. It's a minus 5 because when we rewrite it in scientific notation, we want to put it back 1, 2, 3, 4, 5 places. The other way to do this, by the way, if you want, is we could go 1, 2, 3, 4 zeros, add 1, and that's my power of 10. And the decimal will go right there. So that's basically all I wanted to do with powers of 10 at this point in time. The next thing we do is, what does this all mean when I take a minus log? Because that's the definition of pH. The pH is the minus log of a hydrogen ion concentration. So we look at 10 to the minus 5, and we notice that the log of 5 with a negative before it is turning out to be 5. But it's that exponent that we determine to be the log. That's what the log is. So without the negative up front, it would stay as a minus number. So what we wind up with is a positive number, which is what you're used to seeing pH units in. And that's the long and short of that little deal. So the minus log of the hydrogen ion concentration, as we see here, is equal to the pH. And so in this example, if this were the hydrogen ion concentration, the 5 would be the pH. So basically what you do when you're taking pH is look at the exponent and change its sign. And that does it. That's a minus log. All right, let's go down and look at a little bit more. The pH is equal to the minus log of the hydrogen ion concentration, then it makes some sense that the pOH would be the minus log of the hydroxide ion concentration. Now, you're going to have to slow things down a little bit because I'm going to go kind of fast, and you need time for this stuff to settle in your head. So you need to stop every once in a while and give yourself a break, because I'm going right on here, and we're going to talk about K sub W, which is the K equilibrium for water. And you might want to write this down. And that K equilibrium is equal to this. And we're going to see why that is in a future slide. Moving on, the next thing we need to understand is water self-ionizes. This slide was used to show that, and if you compare to the graphic on page 608, you're going to get a really good comparison to show you what I'm doing here. The only difference is that the stuff up here represents the left side of an equilibrium expression, or an equilibrium equation. Now, down here, we have the right side of that same equilibrium expression. And we should, by all rights, copy this down. And what we're going to do is show what happens with this self-ionization. So, we start out with two water molecules, just like you see in the space fill model that they show on the textbook. And we're going to make this the left side of the equation, and this will be the right side. So to make this work, we have to take a hydrogen ion, come from the left side, which is up here, to be represented properly in the right side, we're going to pull this little hydrogen ion off of here and put him right on there. And that's all that's happening with the self-ionization of water. And this thing goes back and forth. So this will go back here, and then it'll go back here, and it could be the same ion, or it could be a different ion. But this is ionizing back and forth. That's what it always means, that we're going from two waters to a water plus this guy, which is called the hydronium ion, and this guy, which is called the hydroxide ion. Now, you have to realize that two waters will only give you two ions, no more. So we have the hydroxide ion with a net charge that, as we worked it out in class, is going to come out to. And now that I've inserted the pluses and the minuses, this guy went negative because when the hydrogen left, he didn't take an electron with him. It was just a proton. And so when he brought his positive charge over here, this side, which was neutral, is now 1 plus because of this proton. The other thing that happened when he left and took away the proton from this water molecule is that this used to be neutral when it looked like this, but when the hydrogen ion went away, it became a 1 minus. And that's the self-ionization of water. Now, let's look back up here and see what that all means. Why do we talk about that? Because that is the K sub W. It's the K sub W with something that doesn't really belong there. And why don't you stop the recording for just a minute and see if you can figure out what is in this K sub W that doesn't belong there. Welcome back. I hope you took the time to figure it out. This L, and if there is a subscript of S, meaning solid, or the L, meaning pure liquid, they don't go in the equilibrium expression. And we have to substitute for this guy. Instead of the concentration, it's going to be a 1. And so the new K sub equilibrium looks like this, which is what I showed you before, and its value will always be 10 to the minus 14. So that gives us a tool to work with, and let's move forward. Now in this section, what we want to do is see what happens if we put numbers into this. So let's go ahead and put in some numbers. What if the hydrogen ion concentration is equal to 10 to the minus 7? Well, we're going to take the log of this. The minus log of this is the exponent. So when we rewrite this guy as a pH, what is it going to look like? Well, it's actually going to be equal to minus a minus 7, which is what we were talking about before. You're just going to change that sign, and it's going to become 7. And that is neutral. Okay, now let's do the same thing with a POH. The value of the the value of the hydroxide ion concentration is going to be 10 to the minus 7, because if you look at the chart, which you find on page 611, you will see that if the value of the pH is 7, and I've underlined all the pH values with a green line, and I'm underlining all of the POH values with a black line. So let's go right back to here. If the pH is 7, then the POH line, which we're seeing here, is also 7. And so these guys are always going to add up to 14. So let's look up here. I'm sorry, we're going to stick with that one example first. Let's go back. And so let's make this guy what he's actually equal. We are going to take the minus log of 10 to the minus 7, which again is going to be minus a minus 7, because minus 7 is the exponent, and that of course is equal to 7. And you see they are the same. And now we're going to do some examples below that take this just a little bit further. What happens with pH? pH equals 14 if you add in the POH. These will always be 14. And let's use our example from above. We just calculated for neutral solutions that the pH is equal to 7 plus the POH, which was also equal to 7, and we get 14. Now, let's get down here the case of W. The case of W, the hydrogen ion concentration for this guy was 10 to the minus 7. This is the example that we worked up above. And the hydroxide ion concentration was 10 to the minus 7. And now this time is very interesting, because when we multiply powers of 10, we add them. And so we get 10 to the minus 14. Isn't that interesting? 14 here, which is a negative number, and 14 here, which is a positive number. Now, why is this negative? Because these are the concentrations of hydrogen ion and hydroxide ions. And when we add minus 7 to minus 7, we get minus 14. Notice this 14 value keeps showing up here. Okay, here, because the pH and the POH were both 7, they added up to 14, and we had a 14 down here. So 14 is something you want to look for and watch for, because the hydrogen ion and the hydroxide ion multiplied together will always come out to 10 to the minus 14. And we use that to solve for one for the other when we're doing our calculations that we're going to be doing in this chapter. Now let's try this all again. This time let's use a pH of 2 and a POH of 12, which is what they have to be, right? And when we add those together, we're going to get 14 again. And we can see from the chart over here that that does work. Here's a pH of 2, which corresponds to a POH of 12. Now let's go back and let's put the hydrogen ion concentration with a pH of 2. With a pH of 2, what does this number have to be? It has to be the anti-log, which means that the 2 becomes the exponent. And it's going to change sign, so it's going to do a minus 2. And the POH was 12, and so we've got to multiply the hydrogen ion concentration times 10. We take the 12. Whoops. We take this 12, change the sign, and make it the exponent, and that gives us a minus 12. And that works out to 10 to the minus 14. You see how it always works out. And so these guys are very, very closely tied in. In this case, I was doing addition, and in this case, even though I'm multiplying, I'm adding those exponents, which are the opposite signs of these, because we started with these, took the minus log, and became this stuff. So the 12 became a minus 12, became a plus 12, and the minus 2 became a plus 2. So let's look further and see what we have next. I want to show you now something that I did in class that was very, very interesting. And students had a hard time with this because they haven't got everything set in their heads yet, as you probably don't have right now. But what I'm going to do first of all is show you an example of pH plus pOH is equal to 14. Okay, and the example is that I'm going to have a 5 for my pH value and a 9 for my pOH. And of course, those will add up to 14. Now, let's take this guy and let's figure out what the numbers would be to represent this line now. Okay? So I want you to take a piece of paper and write down what you think the values will be for the hydrogen ion concentration times the hydroxide ion concentration. So take a minute and then turn this back on. Now, is this what you got? In most of my classes, this is what the students wrote. And so I guess they were just copying it from up here, but this is not a concentration. This is a pH. This is a concentration. You want to try again? Go ahead. Turn it off. Write it again. Hopefully you tried again, and hopefully you figured out that this is what should have been written. Okay? This is not 5. See, this 5 was a pH, and it has to be anti-logged, which means the 5 has to become an exponent and have a different sign. Okay? Went from plus to minus. This guy, no. Because up here, this was a pOH, and that pOH, the 9, has to become an exponent with an opposite sign, which makes this 10 to the minus 9. And that is the way we get our 10 to the minus 14, not 14. So this, you should cross this out in your head. That's what you don't want to do. Okay? So that should give you a little better hand. Now let's do a little practice. Okay? What do you have for 10 to the minus 2? Say it out loud. What is the hydrogen ion concentration? Okay, so we got to take the minus log of that. All right, pH is 2. Okay, for this next guy, and let's get an arrow on here. So what's the hydrogen ion concentration after we take the minus log to get it into a pH? Well, I hope that's what you got. Let's try again. What is the pH when the hydrogen ion concentration is 10 to the minus 14? All right, let's hope that you got 14. What did we do in every case? We took the exponent, changed the sign, and that became the pH. We took the exponent, changed the sign, and that becomes the pH. Exponent, change the sign, that becomes the pH. Are you starting to feel a little more comfortable with this stuff? I hope so. All right, let's go ahead and... Okay, here we go. Hydrogen ion concentration is 10 to the minus 1. And what does that mean in terms of pH? 1. Very good. Okay, now, is this an acid or is it a base? And if it's an acid or a base, are they highly concentrated or just slightly concentrated? Not concentrated, what you should have said. Well, here we go. This guy's concentrated. Down at a pH of 1, that's a fairly high concentration of acid. Notice it's not a strong acid, but it is, it's not necessarily a strong acid, but it does represent a lot of hydrogen ion concentration. Okay? There's a lot of hydrogen ion in the water. All right, let's go to hydrogen ion concentration of 10 to the minus 7. What do you think we have here? pH is 7. Yes. And this guy's neutral. All right. Let's go down one more. Hydrogen ion concentration, 10 to the minus 14. What do we have here? Yeah, that's right, pH 14. And it's a base that is highly concentrated in hydroxide ions. Okay, hydroxide ions. OH ions. All right, let's go on. This is the way your problems in 18 are going to work out. You have a hydrogen ion concentration or a hydroxide ion concentration given to you. So I'm giving you a hydrogen ion concentration which is going to be changed. Just 3.0 times 10 to the minus 11. So the question is, if you're given the hydrogen ion concentration, find the hydroxide ion concentration. If you're given the hydroxide ion concentration, find the hydrogen ion concentration and tell whether it's acid, base, or neutral. Okay, so for the solution, we're going to calculate on this guy the hydroxide ion concentration, and then we'll tell whether this is acid, base, or neutral. So we're going to start out with 3.0 times 10 to the minus 11. Now, we're going to use K sub W to do the solution for this guy. So we're going to wind up with this thing being 3.0 times 10 to the minus 14. Well, we certainly got that one wrong. We need to fix that. Just a sec. No, the K sub W is always equal to 1.0 times 10 to the minus 14. So what are we going to do? We're going to divide both sides by the hydrogen ion concentration. Okay, and when we do that, we're going to wind up with the hydroxide ion concentration, aren't we? So we're going to go ahead and divide the 1.0 times 10 to the minus 14 by 3.0 times 10 to the minus 11. So 1.0 times 10 to the minus 14 divided by 3.0 times 10 to the minus 11 is going to be the hydroxide ion concentration. So do this in factors. Don't do it in your calculator. Divide the 1.0 by the 3.0, and you come up with 0.33. And then you're going to divide 10 to the minus 14 by 10 to the minus 11. Now, when you divide exponents, when you divide exponents of 10, you're going to be actually subtracting that. So, minus 14 minus a minus 11 changes this guy to a plus 11, and we have a minus 14. And so your exponent is going to come out to 10 to the minus 3. And then all we have to do for our actual solution in terms of the numbers is move our decimal over. Okay, we're going to move the decimal from here to here, and we're going to do that, and then we're going to have to adjust this 10 to the minus 3. Because when we move this 1 to the left, we're going opposite to the direction that this guy goes, which means he has to go up, or we won't wind up as far over to the left as we should be. At any rate, we come out with 3.3 times 10 to the minus 4. Now, what is this? This is the hydroxide ion concentration. So, if you like, you can go back to your chart in the book. When we're talking hydroxide ion concentration, the 3.3 times 10 to the minus 4 is actually going to be between these guys, and so we're definitely in the base area. Okay, so this is a basic solution, just mildly basic, a little more than mild maybe, but it's at a pH of 10 and a pOH of roughly 4. And so we know we have a basic solution. So part of these problems is to tell what is the solution, acid, base, or neutral, and this guy is basic. And you can see here the 3.3 times 10 to the minus 4 and the 3.0 times 10 to the minus 11 for the pH. So the pH, we have to go on the other scale, and the pH being 3.0 times 10 to the minus 11 is going to put it directly above this. And let's go back and let's look at that. See, there it is. 3.3 times 10 to the minus 11. See, we're right in here. And so the pH and the pOH correspond as they should, and we know we're in the basic range. So you're set to do the problems on page 609, and now let's see what we have in store for us when we go back to the other homework problems for tonight that are in the chapter assessment. And I'm actually going to work your problem for you in detail, so you'll have that, and by the time you see that one as well as the example I just showed you, I think you're going to be in really good shape. Okay, here's my last example, and this will be the last thing on this recording. I want you to note that question 87, A and B, are both exactly like question number 18. However, the actual homework problem on page 631, 88B, gets into an area that you haven't had yet, so I really felt it necessary to show you how this works. You're given a hydrogen ion concentration of 5.8 times 10 to the minus 11. Notice this is not a 1. That's where the problem comes in. And you're supposed to find the pH. So here's how it works. It's really very simple the way I have it set up for you, and the estimates are going to get you close enough that you will have no problem understanding what the correct answer is on any test, including the CST. So our first deal is we want to find the pH. So in our solution, we need the minus log of the hydrogen ion concentration. And in this case, since the hydrogen ion concentration is equal to 5.8 times 10 to the minus 11, that's what we plug in for hydrogen ion concentration. Now, when we put that together, we are going to break this guy up. Okay, it's going to be the minus log of 5.8 times the minus log of 10 to the minus 11. That's the easy one. The minus log of this is minus 11, change the sign, and it makes it 11. So, how about this guy? Now we get into estimates. And you are going to want to write down this little chart because this will get you through all of your problems. These are the only ones you have to worry about. This log only needs to be estimated because it is insignificantly small next to this power of 10 business. So what we do, we'll get a value that's close enough by just using one of these three estimates. If it's 2 to 3, notice it's not 1, but it's 2 to 3, we're going to make the value 0.3. If the value is 4 to 6, we'll make it 0.7, and if the value is 7 to 9, we will make it a 0.9. Is it going to be 100% accurate? Absolutely not. But if you wanted to get really a whole lot more accurate than this 0.7 that we're going to get here, what I recommend is that you get yourself a little log table like this. You can get it at my website, and this will translate your numbers right down the line from 1 to 10, depending on what that value is, and you estimate even using this. But this is a little bit more accurate. So what I did was I gave you three key numbers to substitute this whole thing for. And if you want this, you can either, if this is available on the style of file that you're using, which would be Notebook or I think PowerPoint, this should work. You can click here and it will go to this address. You could copy paste this address and that will work. Or you could go to my website, mrwiggerside.com/chem tutorials.aspx, and then select chapter 19 for acids and bases, and the last entry in the bottom of this section will be the link to get you this document up here. At any rate, let's get back and finish this guy off, and then we're done. So the value that we're going to plug in here is going to be that 0.7 that we estimated. Now the other little thing that's a little bit tricky, that is, this is a minus log also. Now on this minus log, we changed the sign of this guy. Now this guy is positive, so we're going to have to change the sign of that as well. So that becomes a negative. So this negative became a positive because of the negative log. This entry became a negative because of the negative in front of log. So we add these guys up and we get 10.3. Now the answer that I see in the answer book, oddly enough, comes out really doggone close. We have 10.24. That's good enough for government work, and it's certainly good enough to get you an A on the CSTs. So that's it, folks. I hope this really helps. See you later.